Hi everybody, good evening. Am I audible? Still audible. Oh, okay, so we will continue with the same session of raster processing in Python, sorry. And we did a few pre-processing steps of cleaning with the no data and masking and then reading the data and everything. So once that part is done, then there is one more pre-processing step that we usually do when we are doing indices calculation, which is called as normalization. So why actually we do normalization is because just let me first rerun everything again. So we have installed and imported everything. We are now loading the uh, two bands. So as you can see here, when we loaded this band pixel values after loading the band, you can see that the values are ranging somewhere between 0 to 13180 or like that. So it is not actually the correct or this will not give you a correct representation of indices, which is always range from, or not always, but mostly lie from -1 to 1 or 0 to 1. So for that reason, we do normalization that we convert these values and fit in between 0 to 1 so that we are just scaling out these values which are in 13,180 and 0 and all these things to some readable format so that you can now better visualize it, present it, create a map out of it. So, but for doing the normalization, what is the formula that we use for doing any kind of a normalization in any of the ranges value if you have? Simple formula is choose the value, means the array of that, then subtracted by the minima value on that lot divided by the maximum value minus minimum value. So that is the formula that we always use for normalization, irrespective of the indices that you are calculating. So it automatically averages out and give you the scale down everything into 0 and 1 after normalization. So to exactly fit into the 0 to 1 scale, we also use np.clip functionality to clip between 0 to 1. What this np.clip will do, let's suppose while scaling, some value can lie between, let's suppose, minus 0.05 or something like that. Or some value can also lie somewhere between 1.2 or let's suppose 1.02. So what this np.clip will do, it will fit in all the values between 0 to 1 only. So the values which will be less than 0, it will make them and fit it to 0, and the values which will be greater than 1, it will make them and fit it to 1. So like that, it will, after doing the normalization, it will fit those values which are little bit off on both the sides, negative side and the positive side, and it will fit and make them into 0 to 1 conversion. It will convert them. So okay, fine. So band 5, we opened it, we read all those values, and then similarly we'll do for band 4. You'll read your band 4 and then read it as an array, means convert them into an array. Once you are done with that, next step was to handle the data type and the no data. So here in at this stage we have learned in the previous session why actually we are doing it, that we are converting into float and dealing with the no data. Or there are multiple ways to deal with the no data. One is that you convert them into NaN, or you directly mask those NaN values and create a mask array and remove them. So it will typically ignore all those pixels which will be in the masked array from your further calculation. So once you reach to this step, now we will use these variable only, red m and nir m, because in red m and nir m, it is now the final array which we have created after ignoring the uh, invalid pixels from your whole data. So since the formula is this value minus min and max minus min, so that means you need the minima and maxima value. So we will calculate the minima and maxima value for both the bands. So similarly, this was the variable where we have stored the array. So red m and nirm for both the bands, we will calculate the minima using .min and maxima using .max. We don't have to use NaN min and NaN max here. Why? Because we have already dealt with our null values. So once you got those minima and maximum value, you have stored it here. If you want to see also, I will just run it separately. And so it printed red minima, red maxima, and NIR minima and NIR maxima is this. So minima is showing approximately around 0.00, but maxima is around, it's more like 37,190. So you will not be able to map it, or no, you will not be able to map it, but you will not be able to fix it in a proper range so that you can create a chart or something like that. So that is the reason we are doing the normalization. So once we have these value, we will directly jump into the formula. We have created a new variable called red normalization and m. In this, what will happen? Just okay. Yes. So we will apply the formula. Red value was main array was red m. So we used red m. Here, red minima minus minima value divided by maxima and minima. So this is what give you a normalized array for red band. Similarly, you will use the same formula for the NIR band as well. So here from these two lines, you will get the normalized array for the red band and for the NIR band from here. Once you get these value from here, red band and NIR band, now we are just fitting it to 0 and 1 so that in case there are some value left in the both the leading and trailing side less than 0 and greater than 0. So you will just simply clip it or make them adjust them into like from 0 to 1. So np.clip force all the values to range of 0 to 1. So np.clip, you have passed the red variable, similarly for the NIR variable, and whatever range you will set here, it will fit the value into that. So we want to fit between 0 to 1, so that's why we have written here 0 to 1. So once you will run this, normalization is done. And if I show you how it looks after normalization, so now your array got converted to these value from earlier array. If I show you, if I just show you this red M, earlier it was like this. This was the array 11381, all these kinds of value were there. Mask was there. But now in NIR norm M, after normalization, we have values like this. It now fits between 0 to 1 now. So once you have adjusted all these values, so yesterday also we have seen directly now you can use the NDVI calculation formula. Though you can directly use this formula like this also. What is the NDVI formula? NIR minus red divided by NIR plus red. So NIR minus red divided by NIR plus red. Directly also if you'll use, you will get the output, no problem. But if you, I'll show you also. You can see that we have got the value for NDVI M as well, like this from 0 to 1. But if you will use the NDVI using this line, inside this line, if you use the formula with np dot r state, divide is equals to ignore and invalid is equals to ignore, what it will do simply that it will handle any kind of error that will come across because of division or because of invalid pixel. So this is just for the doing the safe calculation. Though we have already taken so many steps to make sure that we are ignoring invalid pixels and we are not we are dealing with divisions and all, but still this is also the way to treat them, like with np dot r state. It is coming from the numpy library. Don't basically it is telling the Python that do not crash and just handle everything separately from this. So then if you will do the NDVI calculation using this, it is just a form of doing the safe calculation. Once you get this array, so since you know that in this array, while you are calculating the NDVI, there are no invalid pixel involved. We have simply masked all those pixels where invalid pixels were there by using the masked array. So what we are now doing, we are converting masked array to normal arrays. Why we are doing conversion to normal arrays? Because now I have to plot my input, sorry, uh, I have to now plot my output. So I don't want those gaps to be there in my visualization for that matter. So, and also when you will be exporting and saving this output and opening it in the QGIS, if you don't treat those empty spaces and invalid pixel, it will come hollow. So you don't want that, because there you want the other persons who are now dealing with your output to know that these pixels are NaN pixel. So now you are just simply filling all those masked array with the NaN values. So whenever you will save this output, you will get those invalid pixel as a NaN. So this is NDVI M, means where you've calculated the NDVI dot filled, you have passed np.nan as a type float 32. So you have just converted those masked array into the float 32 type as well and filled them with NaN and as well. So you converted your masked pixels with NaN, and how you have saved them? Saved them as float 32, because obviously all other pixels data type is float like this. So here it is float 64. So I should write float 64. Sorry. Yeah. So it should be float 64 only, because it was like that. Okay. Any confusion at this stage? What we are doing and why we are doing?
Ma'am, if we don't fit the normalized values between 0 and 1,
Yes.
then what will happen?
Then these values will only come, though it will come also the values, like simply it will come like this. You will not be able to get, let's do that without normalization. At that time also you'll get the output. It's not like you'll not be getting the output, but for the representation purposes it will not be looking good, because you won't be able to categorize properly. you will get these very sparse number. Like you can see that here the numbers are very sparse. It is ranging from 0 to 1000, 11,381. So if you have to plot a bar chart for 0 to 11,381, I don't think it will be a good representation of your data set. So that is why we are normalizing it to a shorter span, so that now the spaces between your data set is coarse and it is not very sparsely all over the place. That is the only difference that we are doing the normalization.
No, I mean to understand that after applying the formula of normalization, which is value minus min divided by
Mhm.
max minus min.
Yes.
So after that, why do we need to get that into 0 and 1? If we don't do that, then all
No, acha, okay. That clipping part, this
yes,
clipping
clip.
part, okay.
Yes, yes.
Yeah, this clipping part you can anyways skip, but only problem, and not the problem, but the only thing that you will anyways get the minus value as well. Simple. That is the only thing. If I don't do this, if I just run this and let's find out what is the minimum value for this dot. So top is 1 still and 0. Right now, though there is nothing which is greater than 1 in our data for now, but in some cases it might go 1.2, 1.3. So 1 and 1.3 doesn't make any difference so much when you are presenting the NDVI data. So you don't want that 1.3 to come in your classifications and in your data, in your bar chart. So that's why you are scaling it down, means clipping it down, fitting it into 0 and 1 only, so that the pixel which have value as 1.1 will also be treated as 1. Though 0 and 1 are not the uh, actual values of the NDVI, because the values that we are calculating, this is not representing the richness and the denseness, though we just created a label out of that in the 0 and 1. With the label itself, we will categorize into 5 classes using the equal interval and quantile, and it will just give you a range between that. I hope this point is clear.
Yes. Clipping also is not a mandatory step.
No,
It is.
correct. Clipping, normalization, and let's suppose masking of the array. Though masking of the array not mandatory, I will say, but like an important step, because dealing with the data is important. Though you can still do the calculation just by converting the data pixels into NaN also, because when you do the NumPy calculation, it ignores NaN data while you are doing the calculation. But masking the array is just a more safer way. Similarly, normalizing the data is just a better representation of the data when you will get the output at the end of it. Representation only for the visualization purpose, not, and also for the, let's suppose you are creating a bar chart and all those things. You have the values from 0 to 737,190. How will you plot the bar chart of this? If you create the 5 classes out of this, how will you range it? Will you range it from 0 to 1000, 1000 to 5000, and 5000 to 30,000, like that? So not a good range for the classification, and not a standard practice, I will say. Just that. So these all are the things that I'm mentioning, all are like a safe ways to represent your data, not mandatory steps. Okay. Any questions in this?
No, no.
Okay. Okay, so since let's suppose you got the NDVI, and then now we'll see what is the minimum and maximum value, and then we'll just directly plot the output. So for checking the minimum maxima value for the NDVI output, np.nan minima NDVI, np.nan max NDVI. Why we are using NAN here again and not just minima and maxima like earlier? Why? Because we have now converted our data into the normal array including the NAN values. So for calculating the minima and maxima, I have to ignore NAN values. That's why I'm using NAN minima. So this function will help you ignore the null data while doing the statistical calculation of minima and maxima value. Though in our case, even if I remove this, right now for this data, it will not affect your output. Why? Because there was no data was present in our data. Okay, it is showing me an N because there was some invalid pixel present. Okay, it is showing us NN because there was NN value. We have filled it again. Maybe there was some 1 2 pixel which was invalid. So it's better that we use. In case if there are no data present, then you can directly have that NN minima, NN min and maxima directly with NumPy. So since when you have these values directly here, now you again can get a confusion that if we have clipped it to 0 and 1, then why we are getting minus here and 0.5 minus 0.06, it is less than 0, because that was a different calculation. Here we again did a calculation of subtraction and division. So obviously after this we haven't clipped it to 0 and 1, so that's why we are getting the negative value here. That was just for the NDVI array. This NDVI, NIR and the red band array, we did that scaling part, not for the final NDVI output. Now we'll just plot it. So this plotting we are right now I'm doing using matplotlib. We have already imported matplotlib at the top here. Matplotlib.pyplot as PLT. So we have imported that, and now using this PLT, we will plot our raster data. Right now we are just plotting it in normal X and Y here. So it will look something like that. Here it is fitting into -1 and 1 because we have some negative values as well here. Now, how will you plot this whole data? Simply for plotting this whole data, you will use PLT dot figure. This we have done a lot of time for normal data as well, normal vector data. So this command is same. Creating your figure means creating your x's and all you're creating. After that, now how you will add your data is little different, because while you are plotting the raster data rather than a vector data, it needs a continuous raster color ramp rather than a static color or fill color or boundary color values. So that's why we have imported pyplot.plt, because pyplot will help you give the continuous raster grading colors and all those things. So that's why plt.cm, cm means color map, then you have to define the code. So you can directly give, and there are different codes available. I have shared you the libraries links as well. From there, you can just go and find out different other and explore with the colors of your map. So I have used a very basic color of red and this RDYGLGN, and this will give you this kind of a shade from red to green. Once you have created your color map, now you are now setting cmap.set bad color is equals to light gray. This is simply to give the color to your NaN pixel, so that in case there are a lot of NaN pixel, they look different and they don't become the part of your main range that you are plotting. So you will plot your main NDVI data separately and your NaN data separately. So this dot set bad, what it will do, it will segregate your NaN pixel separately, and you can define a separate color to your NaN values here from this. Once you have defined that, now I just a variable, any variable you can create here, not just I am. Here I am is equal. Oh, I'm so sorry. I am is the key that you need to pass here, where you will create plt dot I am show is the pass. I am show is basically for raster data specifically. We will be using this not for vector data. You will pass your array here in this. By raster data, I mean a array when you are plotting, though we don't plot vector data as an array. So that is why I mentioned that always for a raster data, you will be using IAMShow. You will pass your array here. CMap is the key, means you have to pass your color map. So in this variable, you have stored your color map. You can have a different name at this stage. If you pass CMap1 here, then you can pass CMap1 at this location as well. Okay, the only thing is here you need to write it like this. Like this. CMap1, here you have plotted your color. Then in CMap1, you have set the bad color to right gray. In CMap key, you will pass your color ramp, whatever you have defined. And then here we are passing the x's minima and maxima. This is the static part. This is not coming from your data itself. You are setting your own static x's. Whatever you will set here, it will come into your legend. This particular x's value that you are setting here, there is no relation between this x's and the actual values of NDVI. This is just for the representation that how you want to fit your scale here. So it will just make a equal interval of your scale in this range. And then just plt dot color bar IAM, you have passed your IAM label is equals to NDVI. So in this, what is should be the label of your color bar? So it should be a NDVI, and then you have set your label here, passed your IAM that you have created, what should be the range for what data and for what color map. So you have passed the same color map here so that the color map for your data and the color map for your uh, label should be same. That is the only reason that you have created it like this. And then plt dot title NDVI map. So title will add a title to your plot. Axis off we did because we don't want axis in between, means line in between. If you on this, there will be lines in between. The grids means the grids of the plot will be there. Last one is if you want to save this particular plot as a PNG, then how will you save it? So plt dot save figure, you will be able to save it. Whatever path you will decide for this, it will go and save at that particular location. DPI means how much quality you want and just to fit in properly when you are saving this particular image. Okay, the location is wrong. This folder is not, I just this. Okay. So you'll get the output something like this here. Any questions in this plot? How we have plotted it? Next is also the same kind of a plot. I just plotted the band 4 and band 5 also, but side by side only. First, any questions at this particular step?
No, no.
Okay. So let's suppose if you want to plot two plots side by side, so the how you are gonna plot is same. There is no difference. The only thing that will be different is how you are setting your figure and your axis, means what all things you want to set in between in that particular width and height. So that thing we have to set in this figure. So while you are giving while if you have to give two plots together, so we will be using subplots. Subplots will help me add multiple maps all together. If I keep on adding 2, 3 here, so basically it will keep on adding that how many rows and how many columns do you want in this whole plot, and then you can keep on adding the data into every single row and every single column, and it will just create a map in those rows and columns. So I have written also create a figure with 1 row and 2 column because I wanted two plots, so I want it in one line and in 2 column format. If I make this as 2 column and 1 row, so it will come like vertically, it will come. Okay. So at this point, you have just created your x's here, and earlier we haven't created any kind of used any x's indexes because there was only one plot. Though in our case, right now we have two plots, so we will be using two x's because we have to set that which will go where. So first x's will index always starts from 0, so x is 0, and here you used x is 1. I am show same, I am show, and I am show here. In this, what data you want? I want the data is red, I want the data NIR. In the color map, you have to pass your color. You right now we have directly pass our color. Earlier in this color map, we have passed it using the color map because we wanted a gradient. Right now we don't want any gradient. We want to give a single color. So that's why we have directly passed a static color into our color map at this stage. Then for this axis, what should be the title? For this axis, what should be the title? Earlier we gave the title directly to PLT, like PLT dot title and all those things. Why? Because we were creating for a single map. So we have saved a figure in this PLT dot figure and all those things. So that's why we were creating title in the PLT. Right now there are two axes. So two axes will have a separate title altogether. So that's why we are not giving a common title to the PLT, and we are using axes for giving the titles. So axis 0 dot set title, axis 0 dot axis off in both the cases, and what should the title we gave it here. Then figure dot color bar. In the color bar, basically this color bar we are talking about. How do you want to display your legends at the sides? So I want color bar as well. In the color bar, I want to fit in this particular data in this particular array section. So I pass that also. AX, what should be the AX? AX should be X is 0 in this case, X is 1 in this case. And then this is giving me the fractions. Fractions means how it should convert. This is basically in percentages how you want to break the values that are present in your data set. So that is why we gave that. Padding, padding we have given in both. Padding means padding between the two, the plot and the color bar. And then plt dot tight layout so that it fits in properly, and then just plt dot show for showing the map. Okay. So that is how you can plot two data together, a single data as well with the color bar, with gradients, with static color. Here it have a static color of red like this. It will automatically set it. Now, what if you want to save the output in your drive so that you can use it in QGIS or anything for that matter? For saving the output, one thing that we discussed on the very first session of raster processing was the profile. Profile, what profile will give you? Anybody remember?
All the basic details like the CRS, transformation, etc.
Yeah, so basically profile will give you all the metadata of your raster data. So since we are also saving the NDVI output as a raster data, as a TIFF file, so we need the metadata information as well once you are saving it. So that's why we have saved the profile in the variable called NIR profile at the top. Here, if I show you. Yeah, at this place, once we have opened our band 5, so we have saved nir.src.profile with this variable, and we are only using the profile for the NIR because both of the data sets are coming, both the bands are coming from the same data sets. So metadata is not gonna change. So we'll just copy the same in the output once we are saving that particular output. So we have created an IR profile.copy and saved it in a new variable called NDVI profile. And now we are updating that NDVI profile means that metadata with some new information. So, or new information, or just say that for the being safe, we are updating and passing few things onto that profile where we are saying the data type should be float 32. So it should be Rio. Rio is coming from? Rio is coming from where? It is coming from Rasterio
Rasterio.
library. Yeah, we are have imported Rasterio as Rio. So Rio.float32 to set the data type of this new NDVI output. Count band as one means this band is only one. There are no extra band. We are also giving that no data value should be minus 449.0. So all the NAN value that we have stored as an inverted pixel, it will be now converted into this kind of a pixel value, because once you're saving the data as an output, it will not recognize NAN. You have to give some numerical value to that pixel. So it will be that value. And then later on, when further you have to process it, you can recognize using this and then just convert and treat it accordingly. Compress LZW is just a means to optimize your file when you are saving it. So that is why we are giving compress as LZW here. Standard है basically, it's a standard actually for saving the geotiff file. Then once you have this particular thing, then at this stage, what we are actually doing is replacing all your NAN with no data value. Means we have saved all the no data value as NAN. So we are now converting into no data value, which is this value which we have assigned here in the profile metadata file as well. And then we are actually converting all the values in our array. How we are converting? np.where. What np.where will do? It will find out all the value. np.isan ndvi. So wherever it will find nan values, comma, you have passed this value, replace it with this value, comma ndvi, save it in, and use this array. In this array, find out all the NaN values and replace it with this value and save it in this particular output called NDVI out. And then you will use this NDVI out array for finally saving it as output. The steps that I'm performing here, all these steps are now mandatory. These steps are mandatory steps. You cannot skip it. So with rio.open, so obviously if you have to save any file as well, any TIFF file, you have to open that file. Either you create the path variable and pass the path variable here, or you have to directly pass that string, the path that you have created. Though this path is not available, I'll save it at this location. WY we used so that we are now opening it in the write mode, not in the read mode. So we have learned a lot about write mode and read mode when we were understanding about file handling session. So you know about why we are opening it with the write mode. Once you're opening it write mode, then you are now passing your profile, so it's double star and profile so that it can be attached with your TIFF file. It is a syntax. You have to pass it like this only. As DST means just a variable you are defining while you, every time we open any file, we open it with some Python object reader, right? So that is why we are giving DST and then DST dot write NDVI out comma 1. That in this DST reader object that you have opened at this particular place, go and write this particular array as band 1. That is what we are trying to do here at this stage. So we will now run this. It will be saved in your demo data. Now you can open it in your QGIS or any of the software that you wish to. Yeah, I'll open it later. There's some problem. It's not getting open. We'll move forward. So this is how basically you can save it. Okay. So this was the NDVI TIFF output. You can say the modified time is 22 April 2026, and this was the image that we have saved. PNG file for the map. This also. It is now saved for your visualization. Now we will move toward the last part of any indices calculation, which is the reclassification part. Like right now, you can see that we got all the values from -1 to 1, but actually there is no categorical differentiation between different ranges, and which is densely vegetation and which is mild vegetation, which is low vegetation, like that kind of a category. Because every time you want to do some suitability analysis or you are doing weighted overlay analysis, you will be doing reclassification while giving the inputs as a parameter to that weighted overlay function. So for doing that, the pre-processing step for weighted overlay is always reclassification. So that's why this is important. While you have to do the reclassification, we will always divide the ranges. You can decide the ranges in the classes by yourself. What ranges you want to fit in and how many classes you want to create. Let's suppose in our case right now, I want only 4 classes as such, and those 4 classes will be something like this. NDVI, which is less than 0, will be water, and from 0 to 0.3 will be sparse vegetation. 0.3 to 0.6 will be moderate vegetation, and 0 greater than 0.6 will be dense vegetation. And for all those classes, we are assigning some number 0, 1, 2, 3, and we'll have an understanding that 0 is water, this one is sparse and moderate and dense accordingly. How will you actually create these classes? You have to write it like this. You have to create any variable, simple, any variable name you can choose by yourself. Let's suppose you have created a variable called classes here, and then np.full ndvi.shape. Why we are using ndvi? Because ndvi was our final raster array. This one. So this one was our final raster array. So we will reclassify this array itself. We are using this dot shape. What dot shape will give you? It will create the array and give you the whole shape, and it will give you the shape with the value itself. So what np dot full with ndvi dot shape comma 255 and data type integer will give you? It will give you that it will give you the same shape and size of the NDVI array that you have, the rows and the column and everything. And then 255, why you have used 255 is basically reserved for no data value, that wherever there will be no data, we are reserving that value as 255. And then obviously data type we want as integer 8 for now while we are doing the classification, because we will be converting those classes, those values into, we are assigning every single pixel a value of 0, 1, 2, and 3. So now these values are not the float decimal numbers. So that's why we are giving as integer 8, not as the float 32. That is the reason. Once this part is done, then we are actually categorizing, like how many we are identifying that which pixels are the invalid pixels in this. So if I don't use this symbol, if I just focus on this part, so what this will give you, it will give you np dot is nan ndvi. So it will give you all the true for, it will give you the output in boolean, means true for all invalid pixels. So all the pixels which are invalid, it will give you true for that. But if I use this not symbol, so it will give me the opposite pixels. So that's how I got all the valid pixel, and I have removed all the invalid pixel. This is the not operator that we have used from here. So once you got the valid pixel out of NDVI, then in this valid pixel itself, so from the classes will give you the full array, and then from the classes, basically you are now from the valid in the classes, you are fetching the valid pixel, and then in that you are now creating a logical operator. You are using the logical operator that valid in the valid pixel, choose wherever NDVI is less than 0, like that. So and assign that value as 0 in this. So that is what it is meant by in this line. That is what we are trying to do here. Any questions you have you understood what actually we are doing here? Because everything is same after that, only just we are using different logical operators at this particular place.
Oh, so ma'am, classes is a column which gets formed in the array.
No, not a column. Classes, let's suppose classes is a complete NumPy array that you had for the NDVI, which have same shape of your NDVI array. The your NDVI array means this array that we got as an output. I will just print it here. Let's suppose this was the NDVI array that we had. So what we did, we gave a name or the variable, and we have saved it in that particular class. So we have created a array called classes where we have opened our NDVI array using np.full. What this np dot full will do, basically it will initially treat that all shape and size, all pixel, and it will treat everything as 255. Everything as 255 means every pixel is a no data here. When every pixel in your classes is no data right now, then you have categorized valid pixels from here, and now after fetching valid pixel at this place, you are now replacing and giving a new class value to every single pixel. Means, let's suppose earlier initially uh, classes is no data. Then you found out which pixels are valid pixels. Then you went ahead. Once you got valid pixel array, everything we are dealing with arrays only, there is nothing else. Once you found out what all pixels are valid pixels, then you gone ahead. At this line, what we are trying to do is from the valid pixel, it is now filtering out. In the valid pixel, whatever pixel is NDVI less than 00, this is the value. Give the value as 0. So now in the classes array, we are converting that no data values as 0, 1, 2, and 3 in the array. it is still a array. So once you get this output, if I print the classes, just I'll run this. So you can see that everything now got converted into 0, 1, 2, 3, and 255. 255 is representing no data. Why? Because you have opened your NDVI array and said that all pixel values are 255. You have opened np.full ndvi.shape. You only fetch the shape of the ndvi pixel by means number of rows and column. You fetched, you created a array, but right now if I just run this, just a minute. Right now all pixels are 255, means no data. We are treating 255 value as no data. Then we have we have opened the NDVI, actual NDVI array, used the not operator, filtered all the valid pixel. So it removed all no data from this. It gave you output in true and false. So it gives you true in all the pixels which are valid pixels only. Then from here in the true false, it will fetch that, okay, valid, it will fetch on, we use the AND operator. So true and true will give you the output, correct output. So true and true. So wherever NDVI is less than 0, it will mark and convert those pixel as 0. How it will do? Let's suppose you ran this line, and now if I'm checking this classes array, so it will, though there is nothing 0, maybe it found anything, or there is somewhere in between. Let's check with 1. So it has converted 255 to 1. So that is what it is doing step by step for everything at this stage.
Okay, ma'am.
Uh,
And is the value 255 fixed? We need to use this only, or it can be any integer?
No, you cannot use any integer. 255 is, 255 is the technical number for no data. Minus 49, 255. All these numbers are treated in Python as no data numbers. So even if let's suppose you take this array, the array that we got at the end of this one, and if you just convert it into a file and save it as an output as well, so by default, it will recognize 255 as a no data. Whereas if you, let's suppose you wrote 134, so it will not treat 134 as a no data. It will take it as a value itself, and it will make a different class altogether for that.
Okay.
Okay. Any other questions in this? Okay, so once this classification is now done, now we will plot this classified output as well. So for plotting this classified output, obviously we need 5 distinguished color for doing that color ramp. Though we can use the gradient as well, no issues in that. But for showing you, I am just using different colors altogether. So you can use different colors for 4 classes that we have created at this particular place. So you will use listed color map. So there are multiple ways for doing the CMap. I have used 2-3 ways in these whole session, so that you can choose whatever you want as per your preference and whatever you are comfortable with. Either you can use direct static color names, you can use codes, you can use gradient colors, or you can use this key called listed color map, where you can define all the color as an array. So when you will define color as an array, and then you will just map it against to the, let's suppose, see the example of in the dictionary we used to map it against key and value. So similarly, we have list array here for the color, and then we will create a list array for your classes as well. So it will map against all those classes at this stage. So four colors, and here we have defined the classes as well. I'll tell you later why we have given the classes as 0, 1, 2, 3, 4, 5, because there are four ranges actually: 0 to 1, 1 to 2, 2 to 3, and 3 to 4. That's why we have written five numbers here instead of four numbers. And that's why we given four colors, because the classes are four, means range are only four. So four colors are only needed. So two things are necessary for plotting the reclassified data into Matplotlib. One is the class color, and then your category. You have to define your boundary, means class mapping. You have to define your range. So how will you define your range? From matplotlib.colors. Earlier we imported only matplotlib.pyplot as PLT. We have imported that for basic plotting. But now, though we have to use this listed color map and boundary norm for giving the classes and assigning it using the array of colors, that's why you need to import listed color map and boundary norm. You cannot use listed color map and boundary norm without importing them. Once you have created the classes and the boundary norm is set, now you have to just pass the data. Plt.figure, same like we did earlier. Plt.figure, pass the width and height and size. Plt.imshow, in the imshow you will pass your data. I'll tell you why I use class mask. You can directly pass your array, whatever array you want to plot in the final reclassified output. In the CMap, see whatever color ramp map you have decided, you have to pass that in this. And then norm, whatever boundary or whatever range you have decided, you have to pass that as well in this. So if you will pass color map and you will pass norm, so norm will simply make your data categorical rather than a continuous raster color. And then all things are same. Plt.title for title, x's off for the grids, and color bar. For color bar, we have seen two types of color bar. One using fraction and padding, one without using anything, just directly I passed the IM and then minima maxima, and that just the label. And the third one is this, where you can pass ticks here. Ticks means this ticks, the lines that you can see, this is called ticks. So in the earlier ones, it was not like that. So you can see ticks, you can define where you want what number exactly. Earlier, these number used to come by itself. Here we have defined. It should start from 0, 1, 2, and 3. We haven't written 4. If I can write 4 here, so it will be visible here. And then label for the color bar and plt.show. Okay, anybody wants to try what is happening at this line? I am waiting. At least try few things you can try, not if not all the things.
From the classes array, we are uh, taking the values of no data, which we named as 255, and we're masking it so that it doesn't show in the plot that we're making.
Yeah, so correct. So you were right that we are basically masking the no data value, which is 255. I don't want 255 to be the part of my plotting. So I used np.ma dot masked equal classes comma 255, that masks the pixel wherever it is 255 from my whole data, and then just display it. So that is why we pass this. No other reason. So you can see that now I am having a proper output. There is something wrong with the result because it has masked all the green colors from the output. Okay, because we haven't run this whole classes and it might be taking half input. Okay, now it is correct. Fine. So now you have a proper representation. So if you compare both the result, like the reclassified and the NDVI map that we have uh, saved earlier, so you can see that it is more better visualization rather than better categories of color. If you use more different colors, you'll get more better category and differentiation in the plots here. And at last, simply how you can save it with the same way you can save your reclassified output as well. Just create a profile, copy it, pass it, and instead of you can use LZW as well or deflate as well. So here I have used deflate just for compressing and optimizing your saving process. And while you are saving this output, if you want to have exactly the same symbology and same uh, numberings and codings in your pixel while you are opening it in some different software, then in that case you need to pass this color map as well. So with same thing, you need to open it in the write mode and all those things. Then dst.write classes comma one. Instead of your array, you will pass your classes array here. Now, when you pass your classes array, you will give the class value and the color as well, so that it will be decoded similarly in your JS software. Whatever color you can define, these are the RGB and the color for everything it is defined here. Similarly, you can also define the color. This is the color basically. You are defining against every classes here for 0, for 1, and for 2 and 3. And similarly, it will get open in your software once you will save this particular TIFF file at this stage. So that was it for this raster processing. There's no extra thing is left in raster processing. Now only thing that we will be doing, so whatever we have understood in the previous vector processing and till now in the whole raster processing, you can see that I am doing everything. If let's suppose you want to do this calculation for two areas together, uh, not just for one single area, maybe three areas or four areas, and then you will be having four band 4 and five band 5 files, TIFF files stored in some folder, then how will you do it? So anybody have any suggestions that how will we approach that process? Will you do it independently for every single thing? Like, will you do NDVI calculation, this formula? Will you use it again and again? Where is that formula? Just a minute. Or is there some better way rather than just using this again and again for different study areas? That is our next task also, which we'll be doing tomorrow. But can you think of what we'll be doing for achieving that?
We can create a function.
Correct. So we will be creating functions. Also, we will be using OS library by which we will be and till now, I think in all the session, as far as I remember, we have only loaded the files. We never loaded the folders ever. So in tomorrow's session, what we'll be doing, instead of loading a single file, we will be loading a folder. And then by that folder, we'll be fetching multiple band 4s and multiple band 5s, segregating them, and then we'll be creating batch functions, means functions so that they can be reusable, and then we'll just run that functions on that folder so that you can by a single script, by a single click and running that function, you will be saving by fetching the files from that folder to creating the output folder, saving the PNG files, saving the TIFF file. Everything will be done by just maximum 2 to 3, 4 functions. All the process will be automated. So that is what we'll be starting today. And I have one task for you. I think I have asked in last two sessions as well, that you should explore how to plot this raster data. So now that you have this output of NDVI, you should explore by yourself that how to plot this NDVI using the Folium library. Or if you can come across any better library, you can suggest me also, that I found a better way of plotting this NDVI output in a web map, like interactive map kind of a format. Similarly, like we used Folium, if we should be able to zoom in and zoom out, that kind of thing. So that is a task that you can explore and you should come with it. Okay. Any questions for me?
No.
Okay then. Okay then. Good night. Bye bye.